An offshore pipeline is the bloodline of every offshore energy system. It connects offshore fields, platforms, FPSOs, subsea wells, and processing facilities to one another and to shore. Without it, oil and gas pulled from beneath the seabed have nowhere to go. The pipe disappearing into the water at the back of a pipelay vessel is one segment of a structure that may run hundreds of kilometers across the ocean floor, carrying the entire output of a field every day for decades.
The scale changes how you think about the problem. The gas export pipeline of the Ichthys LNG project runs 882 kilometers across the seabed, diameter 42 inches. The line starts in around 60 meters of water depth and continues to 250 meters at the offshore field. Once welded together, this length of steel cannot be opened, rerouted, or easily inspected from the surface. Most of the pipeline will spend its entire working life completely out of human sight. Every kilometer of it has to survive salt water.
The scale changes how you think about the problem. The gas export pipeline of the Ichthys LNG project runs 882 kilometers across the seabed, diameter 42 inches. The line starts in around 60 meters of water depth and continues to 250 meters at the offshore field. Once welded together, this length of steel cannot be opened, rerouted, or easily inspected from the surface. Most of the pipeline will spend its entire working life completely out of human sight. Every kilometer of it has to survive saltwater, pressure, currents, and seabed movement on its own, often for the entire design life of the field.
The hardest part is not lowering the pipe into the sea. It is turning thousands of separate sections into one continuous structure that no human will touch again for years. Each new pipe is beveled at the ends to match the next one exactly. It is preheated to drive moisture off the steel. An internal clamp aligns the two sections rigidly. Welder systems lay down a root pass first, then a hot pass, then fill passes, and finally a cap pass to close the joint. Every joint goes through automated X-ray testing before the line moves forward. The line that finally leaves the vessel is not a series of pipes bolted together. It is one piece of steel, built joint by joint, kilometer after kilometer.
Continuity at this scale is the entire point. The Nord Stream system required 202,000 individual 12-meter pipe sections welded together for a total route length of 1,224 kilometers across the Baltic. Every section had to match the next one for diameter, wall thickness, steel grade, and weld geometry. A single mismatched joint, or one bad section in a chain of 202,000, could shut down the entire line. The logistics alone, coordinating manufacturing, coating, transport, and pipelay, ran across 5 strategic ports.
The ocean does not care that the pipeline is expensive. Salt water corrodes any exposed steel. Pressure squeezes harder with every meter of depth. Currents try to lift or shift unsupported pipe spans. Trawl gear can drag across the seabed. To survive any of this, each pipe is built with high-grade steel specified for external pressure and wrapped in a concrete coating that adds enough weight to keep the line pinned to the bottom. Every weld goes through ultrasonic non-destructive inspection before the joint is sealed with a corrosion-resistant heat-shrink sleeve and polyurethane foam. Where protection is needed, a dedicated subsea plow cuts a trench so the pipe can be lowered below the seabed instead of remaining exposed on top of it.
All of that integrity has to be built on a moving deck in open water. A pipelay vessel is essentially a continuous production line floating at sea. Single 12-meter pipes are unloaded, beveled, cleaned, and welded together into 24-meter double joints. Each double joint passes ultrasonic NDT before reaching the firing line, where it is welded to the existing main pipeline. Every new weld is inspected again, then sealed, then routed over the stinger at the stern. The pipe descends in a controlled curve into the sea, while the vessel inches forward. Average output for a specialist lay vessel, around 2.5 kilometers of pipeline per day.
The line has to be built on a moving deck, in open water, with no margin for error. A pipelay vessel is one of the strangest objects in offshore engineering, a continuous production facility floating at sea, far from any shore, working in conditions that change by the hour. Wind, swell, current, and weather all act against it, yet the pipe coming off the stern has to arrive on the seabed with the same integrity it would have if it were built inside a factory. Failure on this deck means failure underwater, where no one can fix it.
When the pipeline is finished, it becomes the one object holding the field together. A subsea pipeline connects an onshore processing facility to an FPSO, the receiving end. Once installed, the line carries every barrel of crude the field produces. Unlike ships or offshore platforms, the pipeline does its job without movement, visibility, or direct human access. The entire production system, with all its processing capacity, depends on a single piece of steel resting on the seabed that no one will see again for years. If that connection fails, production across the entire field can.
For pipelines facing the highest internal pressure, manufacturers often choose seamless pipe instead. A solid round steel billet is heated red hot, then pierced through the center to create a hollow shell. Successive rolling reduces wall thickness and stretches the shell into a long tube. Because there is no longitudinal weld, there is no longitudinal seam that could fail. The trade-off is cost and limited diameter range. For subsea line pipe, the choice between seamless and longitudinally welded is a design decision driven by pressure, diameter, and depth.
Where a longitudinal seam is required, the weld itself becomes the critical structural element. For thick-walled pipe, the seam is built with submerged arc welding. An automated welding head travels along the joint, while a granular flux is poured ahead of the arc to cover the weld pool completely. The arc burns under the flux, shielded from oxygen. The result is a deep, uniform, defect-free weld, used here on a pipe component with a 60 mm wall thickness. The same submerged arc principle is used wherever a structural weld has to be both deep and consistent. A pressure vessel rotates on driven rollers, while a stationary welding head lays down the seam. Flux covers the arc. The slag is later chipped away. The exposed weld underneath is smooth, even, and uniform, qualified to carry pressure across the full design life of the vessel. For the circumferential welds joining one pipe section to the next, modern offshore projects use mechanized double torch systems. Footage from the South Stream pipeline project shows two welding torches working simultaneously on opposite sides of the pipe. A guiding band locks the torches to the pipe. Both torches travel around the circumference together, one laying down the lower half, the other the upper half, cutting weld time in half. The system controls arc voltage, wire feed rate, and oscillation pattern automatically, then hands the completed weld off for non-destructive inspection.
A subsea pipeline does not fail as one giant object. It usually fails at a detail, a weld, a coating edge, a bend, a span, or a place where the real world was less perfect than the drawing. In pipeline construction, small geometric errors can accumulate across hundreds of welded connections. The single most sensitive detail at the manufacturing stage is the bevel. Each pipe end has to be cut and beveled at exactly the right angle so the next pipe meets it perfectly when welded offshore. A bad bevel becomes a bad weld, and a bad weld becomes a leak. Modern beveling uses CNC-controlled 3D cutting machines that handle pipe diameters up to 4,500 millimeters and wall thicknesses up to 120 millimeters. K-bevels, V-bevels, Y-bevels, X-bevels, the geometry is specified in CAD, converted to NC code, then cut by thermal torch with millimeter accuracy.
Once the pipe is formed, welded, and beveled, it is still not ready to leave the factory. Each pipe undergoes a sequence of finishing operations. Industrial saws cut sections to specified lengths. Lathes machine the ends to precise dimensions and, where required, cut threads or prepare flanges. Welders fabricate connection points, junctions, and reducers onto the pipe. Some sections pass through industrial furnaces for stress-relieving heat treatment, which removes residual welding stress that would otherwise become a fatigue weak point later. At this stage, the pipe is no longer treated as raw steel, but as a pressure system expected to survive for decades underwater. Then comes surface preparation. Each pipe enters a sandblasting chamber where high-powered abrasives strip away mill scale, rust, and any contamination from the steel surface. Without this step, no coating will bond properly to the metal. The clean surface is inspected, then immediately moved to the coating line. Every step adds a layer of inspection. Dimensions are measured, welds are scanned. Heat numbers stamped at the start of forming are checked again at the end, so each finished pipe can be traced back to the exact steel coil and exact production date it came from. The pipe that leaves the factory is the version the ocean will receive.
The pipe is steel, but what lets it live under the sea is everything wrapped around the steel. Steel handles structural load very well. Steel handles seawater very poorly. Salt water, dissolved oxygen, and electrochemical reactions corrode any exposed surface over time. Currents and bottom debris damage what corrosion missed. To survive decades on the seabed, the pipe is wrapped in multiple engineered layers before it ever sees water. The most visible layer is concrete weight coating, or CWC. A bare steel pipe entering the coating plant already carries an anti-corrosion primer underneath. It enters a rotating, advancing roller system where a continuous stream of high-density concrete is sprayed onto the rotating surface at high pressure. At the same time, a steel mesh reinforcement and a tight outer wrap are fed in parallel, embedding into the concrete as it builds up and locking the coating mechanically to the pipe. A technician walks along the deck of the line, smoothing rough patches by hand, finishing the boundary where the concrete coating ends and the bare end of the pipe begins. A separate inspector probes the concrete with a steel rod to check thickness at marked positions, then scribes a verification mark around the circumference. The pipe leaving the plant is no longer just a pipe. It is a heavy composite structure. Concrete adds enough mass to hold the pipeline down against currents and buoyancy, and absorbs blows from trawl gear or debris that would damage exposed steel.
Beneath the concrete, the anti-corrosion layer is what actually keeps the steel alive. Galvanizing, bonding a continuous zinc layer to steel through a hot dip process, is one of the most common ways to protect industrial steel from oxidation. The principle scales up to pipeline-grade coatings. A uniform, well-bonded protective layer is what stands between bare steel and a corrosive environment.
Pipeline anti-corrosion coatings are rarely a single layer. They are stacks, a primer that bonds chemically to the clean steel, one or more functional middle layers, and a top coat that survives the working environment. Each layer is applied by precision rollers, then driven through a curing oven. Where temperatures of several hundred degrees lock the polymer structure permanently to the surface.
This is where coating becomes a problem the offshore industry has to solve at every single joint. A 48-inch pipeline is built from individual pipe sections, each one already coated in the factory. But the coating cannot extend to the very ends of each pipe. Those ends are bare steel, because that is where the next pipe will be welded on. Every weld therefore creates a gap in the anti-corrosion system that the factory cannot fix. The pipeline may look continuous from the outside, but every welded connection interrupts the original protective barrier. After welding and ultrasonic testing, that bare zone is grid blasted to remove all contamination, then covered with a dedicated field joint coating that restores corrosion protection and provides additional mechanical guard against impacts. Field joint coating is the most failure-sensitive coating operation in the entire project. Standards like DNV RP102 and ISO 21809-3 govern how it must be executed, documented, and quality controlled. A weak field joint coating becomes the corrosion entry point that, decades later, takes the line out of service. Offshore, the field joint coating happens on a moving deck in open weather every few minutes. Inside the firing line of an offshore pipelay vessel, each pipe section is welded to the next while the line steadily advances. The bare welded zone, around 200 to 400 millimeters wide, exits the welding station and immediately enters a coating station built into the deck. A corrosion-resistant heat-shrink sleeve is centered over the joint and heated until it tightens against the steel. Polyurethane foam is then injected into a closed mold around the sleeve and allowed to cure, restoring the full coating cross-section and mechanical strength of the original factory coating. Every step is timed against the lay rate of the vessel. A delayed or defective field joint coating slows the entire pipelay operation, and an undetected one becomes a long-term failure no one will find for years. Now the pipe sections are ready, protected, and inspected, but offshore construction does not happen by simply carrying them to sea. The vessel itself becomes a moving factory, welding one pipe after another while slowly feeding a continuous steel line into the ocean. Inside a pipelay vessel, the pipe sections move along what is called the firing line, a long axis running through the deck where every welding and inspection station is arranged in sequence. A new pipe is brought into the lineup area and rolled onto rollers. It moves into the first station, the facing station, where a pipe facing machine bevels the pipe ends to the exact geometry the automatic welders need.
The pipe then moves into the preheat area where induction torch bands heat the steel and drive off any surface moisture that would otherwise spoil the weld. At the welding station, the next pipe is aligned to the existing pipeline string using a reach rod and an internal pneumatic clamp that locks the joint rigidly from inside. Automatic welder heads then begin work. The first head lays down the root pass. The next station lays down the hot pass, subsequent stations add fill passes, and finally a cap pass that closes the joint. The completed weld then moves to an automated X-ray testing booth where every millimeter of the weld is imaged and reviewed before the pipeline is allowed to advance any further. One bad image stops the entire firing line until the joint is reworked or cut out.
On a specific S-lay vessel, the full cycle takes only minutes per joint. One specialized pipelay vessel has been optimized for pipelines of small to large diameter in all water depths. Pipe sections are transferred on board from a supply vessel, beveled, preheated, aligned, and welded through the standard root-hot fill cap sequence. Each completed weld passes through automated ultrasonic testing to catch internal defects. The pipe then enters the first of 3 tensioners, each rated at 175 tons, which grip the pipe and control its travel speed along the firing line. Past the tensioners, the weld area is grit blasted and reheated, then sealed with field joint coating to restore corrosion protection over the bare welded zone. The pipe then runs out over the stinger at the stern and descends to the seabed in the classic S-lay curve.
The vessel itself is built around the laying system. A modern, fully integrated pipe-laying support vessel is 145.9 meters long, 29.9 meters wide, accommodating 120 crew. The defining feature is the pipe-laying tower mounted forward of the moon pool, rated at 550 tons of top tension, strong enough to hold an enormous suspended length of pipe through the lay process. The tower can fold down so the vessel can pass under bridges with a 48-meter air draft limit on its delivery route, then re-erect once at the worksite. Several vessels of this class were built in series to one common integrated design. At the upper extreme of offshore capability sits one of the largest construction vessels ever built. A twin-hulled vessel 382 meters long and 124 meters wide. Built across 2 years in dry docks in South Korea, then sailed to Rotterdam for final installation of its lifting systems. Designed to lift entire offshore platforms in a single piece and to install record-weight pipelines. The vessel itself functions as a floating heavy construction platform built for offshore work at unprecedented scale. Some operators eliminate most of the offshore welding entirely. That is the principle behind reel lay, supported by an onshore facility called a spool base. At the spool base, individual pipe joints are received, beveled at the ends to the exact welding geometry, then fed into an automated welding line on land.
pass, hot pass, fill passes, and cap pass are all welded together onshore, joining single pipe sections into continuous strings called stocks that are typically 1 to 2 kilometers long. Each weld passes through digital radiography or automated ultrasonic testing. The bare welded zones are grit blasted and protected with fusion-bonded epoxy and heat shrink sleeves for field joint coating, all while still on land. The completed stocks are stored on outdoor racks. When the relay vessel arrives at the quay, the stock ends are tied in together, welded into one truly continuous pipeline, and pulled onto the vessel's reel under controlled tension. The pipe deforms plastically within safe limits as it wraps around the reel drum. The vessel then sails out to the field, runs the reel in reverse through a straightener and a tensioner system, and lays the pipe directly to the seabed at a much higher rate than possible offshore. The trade-off? Reel lay is limited by pipe diameter and by what the steel can survive being bent and unbent.
A single large pipeline project rarely uses one vessel. It uses a fleet. The ICFOS LNG gas export pipeline was built across multiple specialized lay vessels working different sections of the same line. One vessel handled the shore approach inside the harbor. Another handled the offshore deep water section. A third was deployed for shallow water work along the route. At peak production, the largest pipelay vessel in the fleet achieved 122 triple joints in a single day, just over 4.5 kilometers laid in 24 hours, the highest production output that vessel had ever reached since entering service. The lay operation started in 60 meters of water depth and continued out to 250 meters at the offshore field. Concrete-coated pipe was installed for the first time on this particular flagship vessel, which had never before laid a concrete-coated pipeline in shallow water. The logistics behind the work covered far more than just the pipelay itself. The shore-based team had to move project material, pipe joints, replacement crew, food, equipment, and consumables out to the vessels on a daily basis. A single 882-kilometer line is essentially a small moving town, and the work only continued for as long as everything kept arriving on schedule, in the right order, in the right quantities. But the moment the pipe leaves the vessel, the problem changes again. The pipeline is no longer just being manufactured, it is becoming part of the seabed. A pipeline route does not pass over a clean, flat ocean floor. It crosses soft mud, sand, hard rock outcrops, slopes, channels carved by currents, and zones where other pipelines or cables already lie. Before any pipe is laid, the seabed along the route is surveyed, mapped, and graded. Where the bottom is too uneven or too soft, dredging vessels are brought in to reshape it. A cutter suction dredger holds itself fixed on hydraulic spuds, while a rotating cutter head at the end of a long ladder grinds through hard sediment at the bottom. The cut material is pumped continuously through a long floating discharge pipeline to a disposal area on land or a designated dump zone. Every kilometer of channel modified this way is one more kilometer where the pipeline can be laid with full ground contact instead of dangling between hard points. Soft material gets removed by a different machine entirely. A trailing suction hopper dredger sails slowly across the target area with 2 suction pipes trailing behind. Drag heads on each pipe move along the bottom, vacuuming sand and silt up into the ship's own internal hopper. When the hopper is full, the vessel sails to the discharge zone and dumps, rainbows, or pumps the material ashore through pipelines. Where the bottom is hard rock or boulders, the work shifts to a backhoe dredger. A hydraulic crane with a heavy steel bucket sits on a self-elevating platform held to the bottom by long spud piles. Inside the operator's cabin, a digital display shows the bucket position in real time, current dredging depth, target profile depth, swing angle, and reach radius. The operator follows the designed profile to within centimeters, scooping out hard-packed material that ordinary suction equipment cannot move. At this stage, dredging becomes closer to precision excavation than bulk material removal. Each bucket of dredged rock and clay is swung over and deposited into a hopper barge tied alongside. The barge takes the material away. The next barge moves in. The cycle repeats. A pipeline corridor cleared this way becomes flat enough at the critical point of touchdown to receive the pipe at the angle and elevation the route engineers designed.
Where the route cannot be made stable by dredging alone, the pipeline is buried into the bottom itself. A subsea plow is one of the largest tools ever built for this job. Lowered to the seabed from a surface vessel, the plow straddles the freshly laid pipe. Hydraulic grabs lift the pipeline into a roller cradle inside the plow's frame. A surface vessel then tows the plow forward at controlled speed. As it advances, the shear at the front cuts a trench into the seabed to a designed depth and width, and the pipeline is lowered into the trench at exactly the same rate the trench is being cut. The pipe ends up buried below the natural seabed level, protected from currents, trawl gear, and unstable ground that would otherwise create dangerous unsupported spans.
While the pipeline is being laid above, smaller specialist vessels work the anchors below. Massive steel chain links sit stacked along the deck. Hydraulic winches grind chain across the workdeck in slow, controlled lengths. The mooring anchor is dragged toward the stern roller in preparation for redeployment. Anchor handling is less about speed than maintaining constant control over moving loads under tension. Crew members watch from the bridge with binoculars, calling distance to the rig as the vessel approaches. Operations continue through the night under floodlights. Recovered chain comes back onto the deck, coated in seabed mud, and gets washed down link by link before being routed into the chain locker below. Most of the system holding an offshore structure in place remains completely hidden beneath the waterline. Every shift moves tons of steel that somewhere on the seabed are doing the work of holding something massive in position.
Once the pipeline is on the seabed, no diver will ever inspect most of it. That job belongs to ROVs. Remotely operated vehicles drop from a support vessel to seabed depth with cameras, sonars, manipulators, and dedicated tools. At these depths, direct human access becomes too limited and dangerous for routine inspection work. A rotating brush head, deployed by an ROV arm, removes marine growth from chains, pipelines, and other subsea structures so the inspection cameras can actually see the steel underneath. Pressure jets clear sediment. The vehicle effectively becomes the eyes and hands of the crew on the surface. The same ROVs follow the pipeline at touchdown during lay, watching the curve of the suspended pipe as it meets the seabed and feeding the data back to the lay vessel so course and tension can be adjusted in real time.
Even years after a pipeline is laid, the seabed never becomes a finished location. Specialized recovery tools exist for moving heavy structures off the bottom when they are no longer wanted or when something has to be repositioned. The claw is one example. Two 1,000-ton grabbing devices, each 122 feet tall and 112 feet wide, lowered from a surface lift system to retrieve sunken offshore structures from the sea floor.
The pipeline faces its greatest risk at the points where continuity has to be broken and then restored again. A pipelay vessel cannot weld two pipelines together while they sit on the seabed. Connecting two finished sections requires a different operation entirely, a hyperbaric tie-in. The equipment is mobilized at port and transported by vessel to the tie-in location. At depth, the temporary launchers that sealed each pipeline end during lay are removed and recovered to the surface. Pipeline handling frames and lift bags are installed to lift, align, and manipulate the heavy pipe ends. A solo plug is inserted into the upstream pipeline to isolate it. The upstream pipeline end is then beveled subsea to the welding geometry. A taut wire is used for fine alignment between the two ends. The same isolation and beveling sequence is repeated on the downstream pipeline. A welding habitat is then lowered over the connection point and seated. Inside the habitat, water is pumped out to create a dry subsea environment at full water pressure. The pipe ends are aligned one final time inside the dry space. Automatic subsea welding then connects the two pipelines into one continuous system. All equipment is finally recovered to the support vessel.
The same hyperbaric principle becomes essential when the line is already in service and a repair cannot wait for a full shutdown. A life pipeline carrying gas or oil cannot simply be cut into. The repair team starts with surveys. ROVs inspect the damaged section, divers clean the area, support vessels establish position above the worksite. A steel habitat structure is lowered from the surface and seated over the damaged length of pipe, then anchored to the seabed so currents cannot move it. High-pressure pumps then expel seawater from inside the habitat, creating a dry working chamber held at ambient water pressure so the structure does not collapse. Divers enter the chamber, cut out the damaged pipe section, and weld a replacement spool into place using hyperbaric welding under controlled atmosphere. The new weld is then subjected to non-destructive testing. Once cleared, the habitat is reflooded in a controlled way, equipment is recovered, and the pipeline continues operating without ever fully stopping.
A subsea pipeline only becomes a working system at the moment it is mechanically tied into the rest of the production setup. Tie-in is where the line stops being a piece of marine infrastructure and starts moving product. After the pipeline is laid on the seabed, subsea metrology is performed at the end of the line and at the bottom of the riser pipe, measuring the exact gap and geometry between them. A subsea spool is then fabricated to the precise dimensions measured and installed underwater to bridge the two ends. The riser climbs up the jacket structure and is connected to the topside piping system. A jumper hose and bridle cable carry the product, utilities, electrical, and control signals between the structures. The receiving floating vessel is then maneuvered into position by tugs and mooring lines and locked mechanically to the system. Only then does the pipeline finally start delivering product.
Some tie-in and repair pieces have to be cut to the exact field measurement after the line is already on the seabed. Portable CNC cutting machines can be deployed to the worksite by truck, boat, or plane and clamped directly onto pipe up to 4,500 millimeters in diameter. At this stage, even small dimensional errors can prevent a field connection from aligning correctly offshore. The bevels they cut feed straight into the subsea welding workflow. Once the entire line has been tied in, the final step is testing and commissioning. The system is pressure tested to confirm its integrity end to end. Onshore, the gas reaches the receiving terminal, where 48-inch Class 1500 valves regulate flow into the downstream network. Are offshore pipelines old energy infrastructure, or still one of the hardest systems the modern world depends on? The technical body of work behind a subsea pipeline is unusually broad. It pulls together steel metallurgy, weld qualification, multi-layer coating systems, seabed survey and route engineering, multi-vessel coordination, robotic subsea inspection, and integrity management measured in decades. Every stage must continue working together long after the construction vessels have left the area. The same engineering chain that moves natural gas today could move carbon dioxide for carbon capture, hydrogen blends, or future offshore industrial networks tomorrow. Some offshore pipelines operate for decades under constant pressure, saltwater exposure, and seabed movement, without ever being directly visible from the surface. By the end, an offshore pipeline no longer looks like a pipe. It looks like a controlled chain of decisions: steel quality, weld quality, coating quality, vessel control, seabed support, and subsea connection, all hidden beneath the ocean. A single weak section buried deep underwater can force extremely expensive repair operations involving specialized ships and remotely operated vehicles. Even as the world looks for ways to reduce its reliance on oil and gas, every offshore energy system that produces or receives fluid still needs a way to move that fluid to where it can be processed. As long as there is anything producing offshore, there is a pipeline carrying its output to shore or to a central facility. There is no realistic alternative at this scale. Whatever happens to the energy mix over the coming decades, the ability to build and operate infrastructure beneath the sea will remain valuable on its own terms. A pipeline is not impressive because it is long. A pipeline is impressive because it takes thousands of separate points where the structure could fail, every weld, every coating edge, every span of unsupported pipe, every tie-in, and turns them into one continuous line trustworthy enough to disappear beneath the ocean and keep working for decades without anyone touching it. That conversion from thousands of weak points into one reliable system is the actual achievement. What do you think is the weakest point in an offshore pipeline? The welds, the coating, the seabed, or the difficulty of repairing it once it is underwater? Tell us in the comments below. Hope you got something out of this one. There's a lot more heavy machinery and big industrial process work coming on the channel, so we'll catch you next time.